All right. Welcome to Astronomy on Tap, June 2021 edition.
Yay! Welcome, everybody.
I'm one of your MCs for the evening, MC M33.
And I'm your other MC.
Well, we've got quite a few exciting talks for you tonight, but before that, a few announcements.
Yes, let me start sharing my screen here. Oh, where did it go? Sorry, 1 second.
Technical difficulties.
There it is.
Ah!
Got him. Okay. All right. So this is Astronomy on Tap number 37. We've been going a little while. That's a pretty good number. I'm pretty happy about that. The first announcement here is please make sure to fill out our trivia. There are trivia prizes if you fill this out and win. So go for it. Today's topic is energy beer conversions.
Like and subscribe to our YouTube channel so you can stay up to date on all. I lost it. I can never do the YouTube version. If you do allow notifications to be sent to you, you will be kept up to date about when the next Astronomy on Tap is. And give us that sweet engagement.
Yes. Also follow us on all the rest of our social media. So we're AoT _BCS on Instagram and Twitter, and we're AoT BCS with no underscore on Facebook. You can also find out about our events before they happen at astronomyontap.org/events.
Right. So when we go back to doing things in person, hopefully, we will be at our former venue, the Grand Stafford Theater in downtown Bryan, to support them while we're still having AoT BCS online. And honestly, in general, you can Venmo at Jose-Quintana-20 and put Stafford Tip in the description so he knows what it's for.
This is how you can tip your bartenders tonight, everybody. Do it. You can also support us directly by donating. We have a Venmo and a Cash App at AoT BCS. If you donate $15, we will send you an AoT t-shirt that looks exactly like this one.
Right. And we are actually taking a summer break, like most college students do. I know, right? And our next event will be August 18th, 2021. It's the third Wednesday of every month. And this is going to be a hybrid event, it turns out. I am that shocked Pikachu face right now. We'll be having it in person, and it will also be streamed on YouTube.
Exciting. All right, last announcement of the day. Please make sure to put your questions in the live chat on YouTube. Don't wait till the end of the talk. We'll have people moderating the chat and sending those questions to us so that we will make sure to ask them to the speaker at the end of the talk. But go ahead and put them in the chat as you think of them.
And before we get to our amazing talks that we have lined up for you, MC.
Yes.
What beverage are you partaking in tonight?
That is an excellent question. I'm partaking in a Mike's Hard Mango instead of a hard lemonade. It's a hard mango.
Ooh.
It's pretty good. How about you, MCM33?
I am partaking in a Goose Island IPA. It has a bird on the label that you can. There we go.
Oh, there it is. Oh, that's excellent. Beautiful. All right. So our first speaker of the day is going to be Rachel Bezanson. Rachel is an assistant professor at the University of Pittsburg. Her group studies the evolution of galaxies through cosmic time using some of the world's largest telescopes to peer into the distant universe. She's a leading number of observational efforts to catalog. She is leading a number of observational efforts to catalog the properties of galaxies over billions of years, including an exciting treasury deep field uncover with the coming James Webb Space Telescope. Outside of research, Rachel loves to cook, bake, practice yoga, cycle, and travel. That's a lot of awesome hobbies. That's really cool. Yeah, welcome, Rachel. The floor is yours. We're excited to have you.
Awesome. Thanks so much for inviting me. Yeah. Okay, cool. I'm going to share my screen. and then I'm going to talk a little bit about galaxies. Get this started so I know how long I'm blabbering for. So I really enjoy Astronomy on Tap. I've been doing these kinds of talks for years, and you know, while I do miss traveling, I do also enjoy the fact that I can give an Astronomy on Tap in Texas while sitting in my house in Pittsburgh. So today I'm going to talk to you a little bit about how you make the largest galaxies in the universe. They look a little bit like this in the corner, but I'll kind of walk you through this. And this is related to my research, but I'll hopefully talk about it in a kind of fun way because this is Astronomy on Tap. All right, so I just wanted to get started by setting the stage and kind of meeting you where you are. So this is this is a cartoon of the Milky Way galaxy, our galaxy. A galaxy is a big collection of stars and gas and dark matter, and ours looks like this if you could zoom out of it. Now, of course, we can't take a picture like this, but this is what we think. And we live at this little arm, you know, midway through the Milky Way, and the Milky Way is very, very large. So if you traveled from our position at the location of the sun there towards the far edge of the galaxy at the speed of light, it would probably take you something like 75,000 years traveling at the speed of light, the fundamental speed limit to get to the edge of the Milky Way. And these things, galaxies in general, are enormous collections of normal stuff, the stuff that kind of we're used to talking about, stars, or I'm used to talking about, stars and gas and black holes and planets and people and beer and dark matter, you know, things that we're not used to kind of thinking about and talking about. But all of these things are inside of galaxies. And galaxies are very large in physical extent and large in terms of mass. So the Milky Way itself has a mass in stars that's sort of, you know, approximately equal to 50 with 9 zeros, 50 billion times the mass of the sun. And that mass of the sun is 300,000 times the mass of the Earth, which itself is about 10 trillion times the mass of every single human in the human race, if I just, you know, make some kind of gross estimate of, you know, the mass of a person. Or if you prefer, because it's Astronomy on Tap, that's about 2 with 41 zeros pints of beer. And that's just the normal stuff, the stars in the galaxy. But if you were to count the mass in the galaxy that includes dark matter, mysterious dark matter, it would be about 20 times more massive than that. So galaxies are very large. Our Milky Way is very large. But there exist larger galaxies. The largest galaxies look quite different from that picture that I started with. And so this is M87. It's one of the largest relatively nearby galaxies to us. If you ignore that kind of blue, we call it a jet, that's being spit out by the supermassive black hole at the center of this galaxy, this is a pretty boring looking thing. So here's what we know about these massive galaxies. Oh, and you might have seen M87 in the news, say, actually, time flies when you're having fun. So maybe 3 years ago, but you might have seen this image of the supermassive black hole, or really the light surrounding the supermassive black hole in the very, very center of this galaxy. That was taken by the Event Horizon Telescope and is shown for scale by XKCD in this cartoon with our solar system on the inside. So the sun, if the sun were at the very center of that image, and the light is the gas falling around that supermassive black hole, and there's a little circle that shows you where Pluto would be orbiting, and then the location of Voyager 3. So it's kind of the size of a solar system inside the very heart of this galaxy. All right. That's a little bit of a tangent, but it's too cool to pass over. So here are the things that we know about the biggest galaxies. First of all, they're old. And what I mean by old is that they're stars that make up that galaxy. The light that we see is produced by stars that were formed, over 10 billion years ago, basically. And the other thing is that, with a caveat, they're pretty boring. And by boring, I mean they're smooth looking. So I don't particularly think they are boring. I spend quite a bit of my time actually researching these things. But beauty is in the eye of the beholder. What I will say is that they definitely don't look like the Milky Way, like that cartoon that I showed you. And really, they don't look like any galaxy that's actively making new stars. And so we don't think that this is how galaxies, or this is certainly not how galaxies that are forming today look. So one of the kind of driving questions of my research is, how do you make something that looks boring and smooth and old like this? All right. So to oversimplify just a little bit, I went to graduate school, and you open the textbook or the research paper, and there were kind of two previous models to explain how you would make something that's both old and kind of boring looking, not this beautiful disk galaxy with spiral arms that we live in. And the first one I'm going to call the Lady Gaga version. This is the kind of technical term that we often use is called monolithic collapse, but I prefer the Lady Gaga version. And the idea is that galaxies form through a really slow process now, and that's how they form to create disks. But if instead they formed in a much more violent, much more dramatic event early, then they may not form that nice, beautiful spiral disk-like structure that we see in the Milky Way. And so they formed, they make this kind of round, boring, smooth thing. It's very, very large and very, very massive. And then they just kind of age and get old since that point. And the second model, for which the technical term is, a major merger, where you have kind of two galaxies that look like the Milky Way that smash together and destroy all that nice orderly structure. We'll call it the Amy Schumer model. They smash together. The stars are kind of ripped apart in that collision. And that combination of two kind of nice, regular, beautiful galaxies destroys the ordered motions inside the galaxies and shuts off the star formation, stops them from forming any new stars. And then they just stop and they grow older, and we say that they passively age. Nothing else is really happening. Okay, so these were the two models that were kind of dominant in the field when I started my PhD. So in order to test these, you kind of have to look back to that moment, as close to that moment of formation as possible. Now, that moment of formation was, something like billions of years ago. So I don't actually suggest waiting to watch galaxies grow in real time. Very few astronomical objects are studied in real time. But instead, we can use the fact that the speed of light is constant to look back in time by looking into the very distant universe. So the basic principle is here. So if you imagine, I've got a telescope in this observatory on the right-hand side of the slide, and there are two stars, one that's further away from me and one that's closer. The light has to leave, if the light arrives at the telescope at the same time, it had to leave the further star earlier than it had to leave the closer star. And in effect, you're looking back in time further when you see that further star. With galaxies, the distances aren't, light minutes or light seconds, distances in our solar system away, but rather, light travels to us from galaxies for billions of years. And so, we can call this like a cosmic time machine effect, where if you look into the very distant universe, the light had to leave those galaxies at a very early time. And so most of my research involves looking at populations of galaxies at different distances, and therefore at different times, periods of time in the universe, and then kind of connecting the evolutionary dots. Okay. And much of this work up until this point, much of the work in the field has been driven by our workhorse, the Hubble Space Telescope, which is in a cartoon kind of at the left-hand side of my screen. And the Hubble Space Telescope was one of the first observatories that allowed us to get, a beautiful census of galaxies over the last 10 billion years. And it allowed us to ask just things that seem like simple questions, if I look at the things that turn into a galaxy like M87, what did they look like 10 billion years ago? And in my model, the stars are older than 10 billion years old, so that either the Amy Schumer or the Lady Gaga formation modes would have happened before this point. And so actually our prediction before we took Hubble and looked at these objects was really that they wouldn't look all that different. Oops, wrong direction. I can be a little bit more careful. One of the reasons that I know that the stars in these galaxies are old is from their colors. So older things look redder. And so 10 billion years is a long time even for stars. So the galaxies would look bluer and young. That tells me that they look younger. But this was our prediction, and this was very much not what we found. So when we looked to find what we call the progenitors, the things that turned into these huge monsters, they looked dramatically different. They were much more compact. And that implies that since that moment of formation, they've evolved and they've grown over that time period that we expected them to be pretty static. So these are cartoons, I should say. Well, the picture on the left is a real galaxy, but the picture on the right is a cartoon version. Here are two actual images on the same physical scale of a galaxy today. It's my favorite massive nearby galaxy, not for any reason except that I stared at it for a very long time as a graduate student, 8 nights. But on the right, you can see a similar galaxy. They have the same number of stars, roughly speaking. But the galaxy on the right, which is seen, 10 billion light years away, roughly speaking, although that's not strictly the case because the universe has continued to expand. They look just dramatically different. It's like taking all of the Milky Way and shoving the stars into the bulge at its center. All right, how am I doing on time? Perfect. So what do we think has happened? Well, one of the clues to what was going on is that if you look at the overall density of stars, density is just, the number or the mass in stars divided by the volume. Obviously, those densities would be very different. But if you actually look at the density in the very center, these two populations of galaxies look very, very similar. And so what we actually think has happened is that nugget in the very center of the galaxy is formed through some other process, probably ends up looking like, one of the two models that I started with, but then the outsides of the galaxy build up over time. So we say the central core forms first, and then the outer envelope grows up over time. There's a little cartoon of a Tootsie Pop. What you should keep in mind is not the way that you would eat a Tootsie Pop, which would be disgusting candy outside that cuts up your mouth and then chewy, kind of gross, weird nugget in the center, but rather that the nugget is the part of the galaxy that forms first, and then you would add coatings of the sugary candy coating over time. All right. And what physically is happening, we think, is that galaxies don't live in isolation. Really, their neighborhoods, their environments are incredibly important. and much more important than we anticipated. So this is a simulation, a computer simulation of a massive galaxy forming in what we call a cosmological, or just a realistic environment, a realistic neighborhood. And what you can see is that the central galaxy forms pretty early, but over time, that galaxy accumulates many more stars by ripping up its neighbors and assimilating them into their bigger galaxy. So sometimes this is called galaxy cannibalism, galaxies eating galaxies. I kind of like to think of it more as like the Borg in Star Trek, where, you know, all of the stars that once belonged in these small galaxies get kind of pulled into the big, into the more massive galaxy. And this process, we call it this assembly process, is separate from the formation process, the assembly process is separate, but equally as important to the formation process that forms the core, the nugget at the center of these galaxies. So there's a question in the chat. How big of an effect does expansion of the universe have on the merger rate? And that's actually a really interesting question. So the interesting thing about the way that the universe grows, or that structure forms in the universe, is that it forms along essentially what we call a cosmic web. So you should think of like the films that you would see in bubbles on the top of a bathtub, where, you know, there are big bubbles, very big areas of kind of empty space, and those are the things that are really expanding. And then the matter, the stars, the galaxies, tend to live in what we call filaments. And so even though parts of the universe are expanding, the kind of nearby areas around galaxies are, we could say, gravitationally bound. Eventually, gravity mostly wins. Okay. I'm assuming that there will be more questions as we go. Oh, sorry about that. Okay, so I wanted to just say a couple of things and bring it a little bit closer to home, just so that you don't feel left out, because none of us will ever go to M87. It is vastly too far away, but we will be stuck in our Milky Way, and similar things are happening in our very own neighborhood. So for those of you who don't know, this is Mr. Rogers. I might be age dating myself. I am calling in from Pittsburgh. Mr. Rogers is from Pittsburgh. Anyway, so your neighborhood looks a little bit like this. This is called the local group. And right at the center of this is the Milky Way. There's like a zoom in on the Milky Way, and nearby the Milky Way, there are lots of little galaxies. And then there's another massive galaxy, or relatively massive, similarly massive galaxy that's near us, called Andromeda. And it's similarly surrounded by lots of little galaxies. So this is kind of our neighborhood in the universe. And there are two ways in which our neighborhood is very similar to the way that you would build kind of a massive galaxy. So the first thing is that if you look at the distribution of stars in the sky, you can actually see hints of these little galaxies being torn up and assimilated into what we call the halo of our Milky Way, in a very similar but smaller scale version of the movie that I showed you. And so on the left, you can see these are actual maps of stars in the inside of basically like projected against the sky. And on the right is kind of a zoom out of what this might look like for our Milky Way. But I think more stunningly, this is one of my favorite press release movies. So remember, the Milky Way has a neighbor that's very similar in size and in mass, Andromeda. And these two galaxies are gravitationally attracted to one another, and eventually they'll merge. And so here's a simulation of what we think this process will look like. So this is the Milky Way, or a simulation meant to represent the Milky Way galaxy. And it zooms out, and you can start to see Andromeda. soon. Okay, so here's the Andromeda Galaxy. There's time in the lower right-hand corner, and that's going forward from today. So we have these two nice galaxies. They're spinning. That's partly why they're shaped like disks. But eventually, these two galaxies will collide, and slowly will kind of merge together and coalesce, we think, into something that looks a little bit like that second model, the train wreck Amy Schumer model of making an elliptical galaxy, or making a big massive galaxy that's round and boring. Now, I wouldn't worry about this, first of all, because if you look at the time scale in the lower left-hand corner of my slide, none of us, no matter how good, how well science advances in terms of keeping humans alive, none of us will be alive. And perhaps the human race won't still exist at this point. But beyond that, the interesting thing about galaxies is that even though they're full of so much mass, the stars are very spread out. And when they collide like this, the stars just pass by one another, and you don't really get collisions. And so the Earth in this collision would kind of be left alone. And eventually, the view from the Earth would change accordingly. So let's see if I can get this. Yeah, okay. So this is what this collision would look like if you were sitting on the Earth 3 billion, 4 billion years in the future. You would see that instead of having that nice, beautiful band in the sky, which corresponds to the plane of the Milky Way cutting through the sky, the view from the Earth would look much more like that, smooth, boring elliptical galaxy that I started with. So this is my last slide. I'll stop here and see if anybody has any questions.
Great talk. That was really interesting. Give it a couple minutes to see if there's any more questions in the chat.
Until then, I guess. Why were you looking at that galaxy for 8 nights? The one that you said was your favorite.
The short answer is because I was a graduate student. No, the real answer is actually kind of interesting and very relevant. So basically, it turns out that in this, if you imagine the picture from the simulation that I showed, you should be able to see signatures. The image that I showed you of M87 was very smooth and very regular. But if we think galaxies are growing significantly by ripping apart their neighbors, then you should see signatures of those torn apart galaxies. And it turns out that if you stare deeply enough, you can find hints of these non-smooth features in about 70% of galaxies. But if we think that this is kind of a dominant process for all galaxies, you should see them in everything. So we chose the most boring, most smooth nearby galaxy that we could observe from Chile at Cerro Tololo using the 1 meter telescope on Cerro Tololo Observatory. And the trick to getting deep is not necessarily using a big telescope, but being able to image very, very smoothly and uniformly across the field. And you do that by just observing, for a long time. So small telescope, but with really well-behaved optics. So I sat staring at this galaxy for 8 nights by myself, studying for my qualifying exam and taking 5-minute exposures over and over and over and over again. That's the nice version. The sad version is that in about an hour of observing with a new telescope, my advisor sent me an email like I don't know, it was maybe 5 years later that he was using this new telescope and reached similar depths to my 8 nights in like an hour and a half or 2 hours on that telescope. And that was a less nice version of the story. Oh, well.
Next question. And this is, do you really believe that these are boring galaxies, or might they actually be interesting? And follow up, are there really any truly boring galaxies?
Oh, I definitely don't think they're boring. I think that I think that the fact that they're smooth and relatively featureless is deceptive. I think that we understand less about how you make a galaxy that looks like this, and isn't forming stars in a universe that is full of teeming with the fuel for star formation. And then you have a huge gravitational well like this, and it doesn't form any new, it pulls in the gas, but it doesn't form any new stars. Like, I think we understand these things less well than we understand how to make something like the Milky Way. So do I think that there are any truly boring galaxies? No, but that's good because of my profession. But no, I don't think there are any truly boring galaxies. There are just some that are more stunning to look at than others. Usually they're just little blobs.
That's a good answer. Especially at high redshift, they become more
tiny little blobs.
Yeah.
Tiny little blobs.
All right. If there are no more questions in the chat. Awesome. Well, thank you so much for a wonderful talk, and we'll have you back for the burning questions panel.
Cool.
All right. Next up, we have a familiar guest. Please welcome the Cosmic Kid with What's Up?
What's up? How's it going, y'all?
Not bad. What are you drinking, the Cosmic Kid?
I've got a nice glass of some sour mash whiskey. Nice and cool on a hot, sweaty, humid day.
Yeah. All right, take it away.
Will do. Okay, what's up, astronauts? Welcome to What's Up, June 2021 edition. I got some fun things for you to look up in the sky this month. First up, I want to switch up a little bit by discussing some cultural relevances to astronomy. We don't really touch on culture that often. We usually talk about what you can observe, but I want to talk about some of the more historical, cultural things behind some of the things we look at. So tomorrow night is going to be a full moon. It's often called the strawberry moon here in the United States. This is because this is roughly when it's peak strawberry season. And the name strawberry moon actually comes from the Ojibwe people of the Great Lakes region, who would call it the Odeiminigisis moon, which roughly translates to strawberry moon. Some other names for the full moon of this month come in the First Nations people of the United States. The Cree Nation called the Opiniwiwipism, or the egg-laying moon, from the waterfowl that lay eggs around this time. The Mohawk people called the Ohiri hot moon, or the fruits or small moon. And the Cherokee people called the Halui moon, or the green corn moon. So a couple of fun moons, and a couple of fun ways to examine the culture of how different people examine the moon and the significance of certain phases of the moon. July 9th is going to be a new moon, and this is particularly important for some people who cultures that follow the lunar calendar. So in the Hebrew calendar, this is the start of Avat. In the Chinese calendar, it's the start of Lu'yu. And in the Islamic calendar, this is the start of Du al-Hijjah, which is also the start of Hajj, the holy pilgrimage to Mecca that every practicing able Muslim is expected to make at least once in their lifetime. So that'll be starting around July 9th. Of course, it's going to be a little bit tampered down because of COVID protocols, but it is nevertheless a very, very important time in the Islamic calendar and for people who follow the Islamic faith. So just a couple of fun ways and interesting ways to look at how astronomical events affect cultures around the world. The spotlight for this month is going to be the Beehive Cluster. It's one of the closest and largest open clusters to the Earth. It's pretty bright and easy to spot. If you have binoculars, a small telescope, it's going to be a pretty great view. The best time to look at it is going to be around 9 p.m. You're going to want to look due west around 9 p.m. It's going to be setting around that, unfortunately, but it's a pretty beautiful looking cluster, and it's a pretty fun thing to look at. A couple of interesting times to look at it. There's actually some planets that are passing right by it. So on June 23rd, Mars is going to pass right through the cluster in the night sky. So if you look right around 9 p.m., you should see Mars in the same field of view as the Beehive Cluster. And on July 2nd, Venus is going to be very close to the Beehive Cluster. It's not going to quite pass right through it, but it'll be very close to the Beehive Cluster. So that'll be a good time. Another fun thing to look at is July 13th. So Venus and Mars will only be half a degree apart in the sky, making it very, very easy to observe in binoculars or small telescopes, or even just by your eye if you can, see half a degree difference. For reference, half a degree is if you stick your thumb out all the way out, half a degree would be about half the size of your thumb, basically. So not that far apart in the night sky. And again, the best time to observe is going to be around 9 p.m., looking due west. Because they're going to be setting right around 10 o'clock. So 9 o'clock is probably the best time to go observe. Venus Mars also makes a great album by Paul McCartney and the Wings. So if you're interested, I think the only way to do it, honestly, is to be listening to this album while watching and observing Venus and Mars at the same time. And that, my friends, is what's up.
Awesome. Thanks, the Cosmic Kid. That was really good. That was really interesting. Yeah.
On a related note about names, would you happen to know why the Beehive Cluster is called the Beehive Cluster?
Somebody decided it looked like a beehive.
Okay, one of those.
That's basically it.
All right.
All right. Well, next up on our schedule, we have In the News, and we have a new presenter for In the News this month, and that is MC Scatter. MC Scatter.
I think you might have to explain that a little bit, MC Scatter.
I haven't decided how we're going to pronounce it yet because we came up with it like 10 minutes ago. So scatter is a thing that light does, and part of my research has to do with dust, which scatters light. But also, I love ska, near and dear to my heart. And there's a telescope called, well, it doesn't exist yet. There's a telescope array called SKA, which I don't know why everyone refuses to say ska, but we've got a double meaning there. Yeah.
I was once scolded in a meeting for reading it out ska before I knew it was supposed to be the SKA and not ska.
I'd rather say the square kilometer array before calling it SKA.
Yeah.
With many syllables-ish.
I haven't decided if this is a hill I'm going to die on yet, but like chances are it will be.
Good choice.
Yeah.
All right, take it away, MC Scatter.
Yeah, we'll workshop that later. All right, so welcome to In the News. So first things first, we're getting 2 new Venus missions. Very cool, very exciting. The first is called Da Vinci, and Da Vinci is going to study the atmospheric evolution on Venus. There will be 2 flyby passes and 1 probe drop. Now, I read somewhere that the probe is only expected to survive on Venus for like 20 minutes because Venus is a toxic carbon dioxide hellscape. But still, we're going to get really cool data out of that really short amount of time. The next is Veritas, which is the one in the picture. Veritas is going to map the surface and subsurface of Venus. It's going to orbit. So there, it won't drop any probe, nothing's going to land, it's just going to orbit. So, okay, why Venus? We've been focusing so much on Mars lately. So why Venus? So actually, Venus is the most similar planet to the Earth in the solar system. In basically every immutable way, like properties like mass and chemical composition, Venus is almost identical to Earth. Except that Venus is a great example of a runaway greenhouse effect. So the big question is, if Venus and the Earth started out so similar, why are they so different now? Why is Venus's atmosphere 97% carbon dioxide and ours isn't? What happened? Also, this is an actual real life existing example of the runaway greenhouse effect, which is extremely relevant to us given the climate crisis that we're currently facing. These things will launch between 2028 and 2030. So get hyped for those. All right, so next up, the universe is clumpy, but it's slightly less clumpy than expected. The Dark Energy Survey looks for structure in the universe, and Texas A&M is heavily involved with the Dark Energy Survey, so that's pretty cool. This is important because the distribution of matter today has implications for the evolution of the universe, which was touched on in the previous talk. And the result is that matter is distributed more evenly than expected. So it's only by a few percent, but that few percent could really matter. And this work requires follow-up to, make sure it's real, investigate the implications, do all that. But this is what was found. Percy, I know we talked about Venus, we're going to switch to Mars after I, said, why are we talking about Mars? But now we're going to talk about Mars. So NASA's Mars rover Perseverance is done with its testing phase and will move into its data collection phase. We did discuss Percy's landing at a previous Astronomy on Tap. Since then, up until now, all of everything it's done has been just testing itself out. But now we're ready to do actual science. So what's Percy going to do? Percy's going to take some pictures. He will image Mars's subsurface with radar. He will measure wind conditions. He's going to point a laser at rocks to determine chemical content. He's going to drill into the surface to collect samples. And my personal favorite thing that Percy is going to do is he is going to store samples in the robot for future missions to collect and bring back to Earth. How cool is that? Love that. Okay, so on the political side of Astro News, this is, more general, obviously. There are a couple of bills going through the Senate and the House that are giving big boosts to NSF funding. NSF is the National Science Foundation, and it's basically the organization that distributes science funds. And more money for science is nice, but this budget amendment is basically just because the US is trying to compete with China. And the bill contains a lot of provisions restricting China's access to US intellectual property, which is really bad for international collaboration. So the House bill is basically the same. It's a little bit less money. And it also places a bottleneck on collaboration with, I have a typo in there, that should say Russia, with Russia, Iran, and North Korea. And for reference, the current NSF budget is about $8.5 billion. So if these bills pass as they are now, this plot is the maximum case scenario. Their budget will over double. But unfortunately, it is largely because we're trying to be competitive. All right, so it is Pride Month, by the way. It's June. Happy Pride. So we're going to discuss trans rights for scientists. So something happened this month. So what happened? 2 astronomy journals declined to retroactively change a trans scientist's name on her previous publications when she contacted them and asked them to please do this. Why does this matter? This matters because it forces trans people to choose between outing themselves, abandoning credit to their own past work, or publishing under a dead name. Now, it's very, very important that we all affirm trans people's genders. But in addition to this, this causes a bunch of professional issues. So if you're, for example, if someone chose to abandon credit to their own past work in order to avoid being dead named, then that creates a bottleneck on their career that cis people wouldn't otherwise have. Also, it's worth noting that a 2016 APS, which is the American Physical Society, survey indicated that half of trans physicists work under discriminatory conditions. None of this is acceptable. So, Astro Twitter rallied. What we do best. Emily, a grad student in Germany, spearheaded this letter, this open letter to one of the journal's board of directors. The journal was Astronomy and Astrophysics, about their lack of name change policy for trans academics. It's a very good letter. If you come across it, I recommend you read it. And as a result, several astronomy databases and publications now have explicit written policies allowing retroactive name changes, and several others are in the process of reviewing their policies. Now, this is bigger than astronomy. This matters for all of science. And one really great thing that happened in March is that Elsevier, which owns, is that how you pronounce it? Elsevier or Elsevier? I don't know. I just realized I've never had to say that out loud. I've only ever read it and written it. Anyway, they own over 2,500 journals across disciplines, and in March implemented a policy allowing retroactive name changes. So that's great. That's a lot of journals. And you can see, go to this URL that I've made for you all, text.ag/name change, for a living document that lists journals and their retroactive name change policies. And it's continually being updated as more information comes in. This is maintained entirely out of the goodness of the heart of an astronomer somewhere in Europe. So it's not like formal, but it's an awesome document. I love it. That being said, all of this is wonderful, but there's still a lot of work to be done to make science inclusive for trans and non-binary scientists. So we shouldn't look at this and say, everything's great now. Yeah, that's all. Oh, by the way, the scientist whose story kicked off all of this, her name has been changed in one journal, one of the 2 that she contacted, and the other one is reviewing their policy. So, result TBD on that one. But yeah, that is all. That's what's in the news.
Thanks, MC Scotter. Yeah,
Thank you for a great update.
Especially important.
Yeah, definitely. We do have a question for you from the chat.
I'm ready.
This is, could we have a Percy on Venus?
So I think part of the problem with putting a rover on Venus is that the conditions are so hostile that it would kind of just die, which is why the probe will only last like 20 minutes or something. Yeah, I don't have a complete answer for that question. I don't know what would be required on an instrument in order to have it survive on Venus for some significant amount of time. But the reason we haven't done that is because Venus is very hostile.
Yeah.
Good
It's
answer.
very pretty though.
Yeah.
This is also true.
All right. And for our, well, actually, before we get on to our next event, Please be sure to do trivia if you're interested in that. The link is in the description of our video, which you should be able to access because you're presumably watching this on YouTube. Please do fill it out. It's a very fun topic this month, and if you score well, we will send you cool astronomy swag.
Cool swag, free swag.
Even better.
All right.
All right. Next, we have a very fun event that I really do like, our Burning Questions panel. So all the speakers you've heard before are going to return, and they will be joined by Justin Astroman Cole, one of the graduate students in astronomy here at Texas A&M.
Hello, everybody.
Welcome back.
All right, so for those of you who haven't maybe heard of this event before or attended this event before, the way the Burning Questions panel works is we have compiled a list of astronomy questions that we've got from Astronomy on Tap attendees and also from the chat, surprise. All of you on the panel have not seen these questions before. So you are allowed to look some things up if you would like to put a concrete number on your answer, but generally the idea is you answer these off the cuff. Is there anything to add, MC?
No, I think that's it. Yeah, the general rule is no foreknowledge of the questions, expect the unexpected, and have fun. Cool.
All right.
Do you want to take the first one?
Oh, yes, thank you.
Go for it.
Yeah, the first question comes from our chat, from Paulina. How old is the oldest galaxy?
I'm guessing that's for me. We don't actually know. So there are two ways that you can figure out how old something is, right? You can look, and you can essentially do like an archaeological approach. So you figure out kind of how old the stars are, and that gets harder and harder the older something is. So it's hard to differentiate between something that's 12 billion years old and 11 billion years old, let alone something that is 12.1 billion years old and 12.0, right? That's just something that is extraordinarily difficult to measure. Whereas, something that is 1 billion years old versus something that is 500 million years old is actually pretty easy. So like our ability to measure that kind of finely tuned archaeological approach on figuring out how old something is limited fundamentally. But, so, the oldest things are probably somewhere between 12 and 13 billion years old. The universe is 14. I mean, we don't really know. The other way you can do it is you can look back in time, look into the distant universe, and look back in time and see how early galaxies start to emerge. And we have started to find hints that galaxies show up, big galaxies or significant galaxies show up, hundreds of millions of years after the Big Bang, which is well before we expected to see them. The James Webb Space Telescope, that thing, should it not blow up, knock on all of the wood, I think we'll answer that question much more conclusively.
Awesome. Does anyone else have anything they want to add before we go to the next question? All good? All right, next question. Why do so many people have the expectation that other life in the universe would be able to communicate with us?
I can try to take this one. I always think like this question always makes me think of like Gothic novels and like fear of the unknown, and like, if aliens are way different from us, like that's scarier than if aliens are like us, and I think one of the scariest things, at least for me, is like, if we are the smartest, if we're the most intelligent species in the whole universe, my God, we're in so much trouble. If we were number one, no, please. But like I saw something the other day that was like one of the scariest things is we could find more humans. Like that would be terrifying if we just like found a planet of humans. And so I just think that people are like afraid or don't want to like think about humans being like the apex predator, if you will, of the universe or the galaxy, whatever.
I also think this is leaning more into psychology and astronomy, but I think humans also have a tendency to anthropomorphize things, which has been well documented, and it's just a way to make things seem more relatable, to be able to empathize with different things. And so it's a lot easier to imagine aliens that we can communicate and hang out with than aliens that are something beyond our imagination, because how would you imagine that in the first place? And then, of course, there's the fact that, if you're making a Star Trek TV show in the 60s or whatever, it's a lot cheaper just to have humans in green face paint than to actually have some expensive CGI and make up entirely different ways of communicating and stuff like that. And so that's just sort of ingrained in our cultural consciousness at this point.
I have something to add to that doesn't necessarily, it's not really an answer to the question, but it's an elaboration. This is a comment, not a question. So not only would another alien species have to exist in the first place, but they would have to exist at the same time as us, with technology advanced enough to communicate with us. Sorry, there are flies in my apartment. Civilization doesn't last very long. We would have to overlap before, they couldn't have destroyed themselves yet. All of that, it makes it so improbable, I think, that we'll really make contact. That's a really pessimistic view, but it's really a lot of things. We haven't had technology very long. And the lifetime of the universe is so much bigger.
All good answers.
Yeah, I've got so many more questions. So, and this one brings us back down to earth and is possibly kind of spicy. Maybe everyone will want to have a go. Who is the most influential astronomer of all time?
Jimmy Neutron. Send tweet.
Whoever came up with the magnitude system.
It's infamous.
The Greeks and no. Modern astronomy? I mean, you could go for someone like Cecilia Payne. It wouldn't exist.
Rachel, could you elaborate more for those in the room who might not? I'm forgetting the train going by.
Yeah. So I don't know how to point to just one person, but there are some people who have made these kind of fundamental game-changing discoveries, and Cecilia Payne was someone who, I think people expect to hear Albert Einstein. But Cecilia Payne was, made fundamental contributions to our ability to understand stars, the light coming from stars, the stars that are the building blocks for, our galaxy and, honestly, us to some degree, right? And so, I don't know the most influential, but I think that that is not a name that comes up very often, and I think fundamentally super important to our understanding of modern astrophysics.
Anyone else want to have a go? That's a great answer. I think I really just want to add really quickly, because I have feelings about this too, that I think of big misunderstanding in people outside of science spheres is the idea that you can have a lone genius operating in science who does a lot of science by themselves, and that's just not how anything in science works. And I mean, you could probably still argue that like for one person to be more influential than others, but overall, like it's so collaborative, and those collaborations tend to get so much more done than anyone sitting in an echo chamber, no matter how smart they may seem. Yeah.
And I think that that is only increasing, right?
Yeah,
The collaborative nature of astrophysics compared to almost any other discipline is international, like fundamentally international and collaborative in a way that most other scientific fields are not. And I think it's one of our strengths, but it is hard to point to one person because of that.
Honestly, that's just more evidence for whatever Greek philosopher came up with the magnitude system, because nobody could tell him no. And we've all kept up with it for thousands of years.
Good point. Good point. All right, awesome. If there's nothing else, next question. What is the next big new advancement in astronomy?
I'm gonna be dramatic and just say aliens. Like, I mean, all right, so maybe as an astronomer, it's like, we can discover lots of, we can like make discoveries. Like James Webb is gonna get, that's one of the nice things about astronomy is like we think we know what we're gonna see when we look out there, but like when we run these experiments, like staring at the sky, we never know what we're gonna get. But like we have a really good idea, and I think like the next most shocking thing that astronomers could find would be aliens, or like a planet with obvious signs of life, even if that life is like non-sentient life. Like that would be incredible. But maybe that's just me being like a pessimist about my subfield.
I think it's going to be something really obscure that only astronomers really understand. Like, I think the last big thing was probably gravitational waves, which is basically just proving a 100-year-old theory, but the average public has no idea what that means or how it works or anything like that. But all the scientists got really, really nerdy and excited about it. So I have a feeling it's going to be something like that again, where it's like some obscure theory that's been proven that we all get really excited about, and the average person has no idea how or what that actually is.
I do think that like big discoveries are possible in astronomy in a way that they aren't in some disciplines. Like we don't have experiments. We sometimes use that term, but we don't control the initial conditions. Full stop. So we're not experimentalists. I never say I'm an experimentalist. I'm an observer, right? You don't control. You don't know. And so I think there is parameter space that we haven't explored, and I think that's why it's important to have some things where it's just like, I don't know, I'm just going to stare into space and see what we see, and maybe that staring into space shows us aliens, and maybe that staring into space, I mean, as opposed to gravitational waves, the discovery of gravitational waves, that was an experiment, really. I mean, I think that future studies will kind of be more observational, but like fundamentally LIGO, which is the observatory that they use to discover gravitational waves, like that was an experimental project until it became an observatory. Now it's more observational, and they'll see what they see. There will be some discoveries there. It won't just prove that GR works, I think.
All right, I've kind of counted to 7, which I think is how we'll know when a question is up. Okay, this next one, kind of fun, and it has 2 parts. How do you feel when you're called an astrologist? And part 2, do you believe in astrology?
I mean, as far as how I feel when called an astrologist, I don't care, honestly. Like, someone misspoke. Who cares? And do I believe in astrology? Do I believe that the planets and the stars predict our futures? No. But do I believe that people can grasp onto these concepts from astrology to use them as guidance and apply them to their own lives in very legitimate ways? Yes.
Right. I've also counted to 7.
I was gonna
Yeah, go ahead.
Just real quick. Like, I've never cared. My cousin calls me an astrologer on purpose, because she thinks it's funny. But my dad has accidentally called me a cosmetologist before. And like, I don't even study cosmology to begin with. So that's like the closest anyone's like ever been to calling me an astrologist, I suppose. But I totally agree with MC Scotter that like the placebo effect is very powerful. And if you can use that, why if it works, it works.
Once the reverse thing happened to me where my friend was talking about their friend who was actually a cosmetologist, but they said cosmologist. And I was like, you mean me? If you're watching, hi.
Sorry, I concur with the opinions presented. Just also don't use astrology to deny people housing. I'm looking at you, California. I don't like it. Don't let that actually impact your daily life like that.
Good answers. All right. Next question. If all of the matter in a galaxy came together, would it be able to burn as a star?
So what you're talking about has been theorized, not all of the matter in galaxy, but large amounts of matter coming together at once has been theorized in the early universe when there was a high density of matter. The theory is that they would just directly collapse to a black hole, and that's probably what happened if all the matter in galaxy would collapse down at once. It wouldn't be able to burn a star, it just immediately turn to a black hole, basically, or roughly immediately. I mean, there's probably a time scale to it, but that's what would happen at that scale of mass, is it would just turn to a black hole immediately. And that's where we think a lot of the supermassive black holes probably started out. Maybe in the early universe, there was a big cloud of gas that just immediately collapsed down to a black hole once it got dense enough. And that's where supermassive black holes eventually grew out of, the seeds for supermassive black holes. But we haven't seen direct evidence for that just yet. So that'll be an exciting thing to look for with, for instance, JWST to try to find evidence for that.
All right, thank you. Next question. What is a parsec, and is Star Wars using it wrong?
A parsec is a distance of measurement, and Star Wars is not using it wrong because the Kessel Run is dangerous and fraught with like crap in the way, right? So the reason you don't take the short route is because it's dangerous. So if you can do the Kessel Run, which strictly is from point A to point B in a shorter amount of time, you've done a better. Sorry, I said time. I just like in a shorter distance. Usually, this kind of stuff is measured in time, but in this case, it's distance. Just make all the units 1 and measure everything in EV, and you're okay. Anyway, so yes, it's correct.
They actually fixed that in Solo, but nobody watched Solo, unfortunately. It was an okay movie. But they do specifically show the Kessel Run as being them taking a shortcut through this very treacherous journey, and that's how they managed to finish it so quickly, not because of time, but because of distance. Although George Lucas in the original Star Wars was definitely thinking that it's time, probably.
I'm pretty sure that this is like a retroactive fix.
It's definitely a retcon, but you know what? It's fine. It's harmless fun. But
worked out.
A parsec, we should probably explain what a parsec is, though. So parsec, I forget the exact distance, but it's short for parallax arc second. So parallax is the concept that, if you look at an object from two different angles, for instance, if you hold out your thumb, close one eye, close the other eye, you'll see your thumb shift in position. So that's the idea of parallax, basically. So you observe a star from Earth from, say, summer, and then observe again in winter when you're on the other side. 3.26 light years. Thank you, Rachel. So a parsec is 3.26 light years. So if you observe an object from summer to winter, so on either sides of the sun, you should see the stars sort of shift in angle in the night sky relative to other things. That's called a parallax. And so if the parallax is exactly 1 arc second, so you divide the sky by 360 degrees, divide by 60 minutes, divide by 60 seconds, you get arc seconds. And then if the parallax is 1 arc second, then it is 1 parsec away. You do a little bit of trigonometry. You got a right angle from the sun and the Earth. You get 1 AU on the baseline. Your hypotenuse, I guess, whatever, you figure out that angle from the parallax. And then the distance from the sun to the star is going to be 1 parsec, or 3.26 light years. So yeah, that's the quick version of what a parallax is.
Awesome. Good answer. Okay, so next question. Will the new generation of astronomical instruments ever reach the furthest corners of the universe?
It sort of depends on what you mean. The universe has no corners. And so will we ever see the Big Bang? No. Right? The cosmic microwave background is the kind of fundamental limit, like a cloud edge hard limit. So we will never see that starting point. With electromagnetic light. There is some hope that possibly you could reach past the haze with something like primordial gravitational waves, but that's a little bit. So light, no. We'll never actually see that furthest distance. But we'll get pretty close. And we have imaged the cosmic microwave background.
All right, we have time for one more question. This one's maybe a little more serious than the rest and more sociological than astronomy. But what is the explanation for the appearance of some people who believe that the Earth is not round and that man has not reached the moon?
That's a loaded question.
So, yes, there's a documentary on Netflix about flat earthers. And it's really good. Honestly, I think it's a genuinely good documentary. And I think the number one thing that I took away from it to, what's relevant to that question is that there's a very strong sense of community within the flat earther community. And I think that's important. And that's something that draws people in. Obviously, we're social creatures. We seek community. And they sure do have that.
I think another important thing to remember is that a lot of these people, they're not stupid people. A lot of these people are really, really smart. They just have a different belief than what's commonly accepted and what's commonly known. And they just have to dig into certain beliefs. And what often happens is that the more you try to disprove them, the more they tend to dig down into the beliefs, because it's something that they hold very close and very personal to them. And then, a lot of people will then just give up and just label them as being stupid or idiots or whatever. But that just doesn't help the case anymore, and that just sort of further aggravates things, unfortunately. So that's another thing I want to really quickly dispel, is I think these are not stupid people or anything like that. It's just they have certain beliefs that differ from what's commonly accepted, and attacking them isn't necessarily going to help anything.
I think it all kind of comes down to like trust. Who do you trust? What do you believe? And like when you dig down to the core, right? Like I'm not going out and testing everything that I hold to be truth, and you don't, and nobody does, right? But the basic premise is that I trust the scientific method, and I trust that the peer review system kind of will evaluate, will assess, experts will assess scientific claims. But that when you dig down to it, that's a core tenet that I hold. Now, not everybody, when you dig down to what they trust and who they trust, relies on the same sets of, basic fundamental beliefs. And that's not like a less than, but it's definitely a different. And I think it's something that we kind of, as scientists, have to think about how to approach without attacking, without criticizing, without labeling as, less intelligent, but really just kind of coming from a different place. It's important. I mean, in astronomy, it's important. It's important for believing that the Earth is flat. But it's all the more important when we're in the middle of a global pandemic and we're trying to convince people to get vaccinated. So I think it's a really, really important question, and one to which I don't know the answer.
I'd like to add, I think it's important to recognize that science is not the end all be all ultimate truth of everything, right? It is to some degree faith-based. And like Rachel said, we have to trust and believe in things like the scientific method. And I don't think, how do I want to phrase this? I think the idea that science is the absolute truth and is just real, end of story, is misguided. Also, we can't do anything unbiased. We are human. We cannot remove ourselves from the human perspective. That's all.
Yeah, I think that's true. And the other thing I think that is really uncomfortable, just like fundamentally uncomfortable about science and the scientific method, is you cannot prove anything to be true. You cannot. And so everything is taken on faith, right? You can disprove things, but the scientific method cannot prove anything to be true. And I don't think that's comfortable for many people. And I when it comes down to it, it's not comfortable to me when I think about it too much. But it is true. So if somebody comes promising you truth, then I understand that that's attractive, because you can't prove anything to be true with science.
I think that's especially true with like space related things, because like people are usually pretty accepting of, like Newtonian gravity still works if the Earth is flat. That still works. People are like, yeah, Newton, he's a smart guy. And I've never really had run-ins with like any flat earthers, or had confrontations, I guess, with anyone who was a flat earther. But I've definitely had conversations about the moon landing. And that definitely just comes down to faith. Like a lot of people will use like the flag was waving, the moon does not have an atmosphere, therefore they did it on Earth. And I'm like, you know what, that's totally fine, but I am willing to accept that there was a little, motor that made the flag go back and forth. I'm willing to accept that, but a lot of people aren't, and like that's totally okay. I use that example because that's the one I get like the most often. For example, my dad doesn't believe that the moon landing happened, even though he watched it on TV when he was 14. So, you know, yeah, I think it's just especially true in like astronomy and space-based sciences where like, I don't know, it's just pictures. Like we're doing all of this from pictures. And
You can't touch it.
Yeah.
Thanks, everyone. That was really thoughtful answers. And yeah, that was a hard question, not gonna lie.
Yeah, great discussion. Yeah. Okay, I think we need to wrap up the panel and move on to trivia answers. So thank you all for being on our Burning Questions panel. Great job, everybody. And thanks to our amazing audience for submitting amazing questions. Those were a lot of fun. And yeah, we'll get on to some trivia.
So, reminder, trivia this month was energy beer conversions. Very apt for an event like Astronomy on Tap.
Indeed. All right. So, energy beer conversions. Question number 1. All right. So our hypothesis here for this entire thing, the thing we're taking at face value here is that if you look at a bottle of Blue Moon beer, it will tell you that it has 170 calories. Now that's a unit of energy. So we can convert that to a more commonly used SI unit of energy like joules, and then we can compare that to how much energy various astronomy things take up. So let's create a unit called 1 blue moon. That blue moon has the amount of calories that blue moon has. And we want to know how many blue moons of energy the International Space Station uses in 1 second. And the answer to that question, this surprised me, is 0.1. It's not a lot. Only 0.1 blue moons per second to run the International Space Station. Yeah.
Wow. That's cool.
Yeah.
But not as cool as sending a ferret to space, evidently. Wait, that's a ferret? Yeah, that's a ferret.
Yeah, it's a ferret.
Okay. So how many blue moons of energy is required to launch just 1 kilogram into space? 50!
50 blue moons. Yeah, so a kilogram is not that big. And to be fair, rocket fuel that we use is generally a bit more efficient at converting that energy into, you know, blast off juice than when we drink a blue moon. So yeah, only 50 blue moons to send 1 ferret to space. All right, JWST, NASA's new telescope, which is hopefully launching later this year, fingers crossed, is going to have some solar panels which will convert energy to power the telescope. How many blue moons of energy can those solar powers provide each day? And the answer is 250, enough to send several ferrets into space.
NASA's new space program. They've been keeping a secret. Anyhow, question 4, coming back down to Earth. About how many blue moons of electricity does the average American household use in a year? I'm very scared to see the answer. Okay, not as bad as I thought. 55,000.
Could have been worse. Could have been worse. Yeah. All right. So brown dwarfs are objects that don't quite have enough mass to form stars, which is why we sometimes call them failed stars. So they don't fuse hydrogen into helium. But how many blue moons of energy do they actually give off in 1 second? And the answer is 5 quadrillion blue moons. So we took quite a jump up here, 5 quadrillion blue moons. So even though they're not fusing, they still radiate a lot of energy every second.
Oh boy. And if you think that's a lot, how many blue moons of energy are released each second by the sun? 500 quintillion blue moons, which is 5 followed by 20 zeros, if I'm remembering my
Yeah, yep, correct. Yep. Yeah, so I mean, had to be a lot more than the brown dwarf. All right. 21 centimeter line emission is a famous emission from radio astronomy. But how many blue moons of energy are required for one electron to make this transition? It's going to be tiny. It's going to be meaninglessly tiny. It's 1/millionth of a blue moon.
I love the powers of 10 that we were exploring here.
It's a good time.
Question 8. Coming back to those jets that you saw in Rachel's talk. How many blue moons of energy does a typical quasar release every second? And 10 decillion. Okay, I'm glad I didn't have to say the other two options, but 10 decillion, 1 followed by 34 zeros.
It's a lot of energy. All right, but how many blue moons worth of energy are released in a type 1a supernova? The answer here is 200 undecillion blue moons. So 2 followed by 38 zeros, which is a lot of blue moons of energy.
And finally, how many blue moons of energy are there in one blue moon?
It's not a trick question.
This reminds me of what happens when you Google how bright is the sun, and you get 1 solar luminosity, which is basically 1 times the brightness of the sun, which thanks, very helpful, Google.
Yeah. Yep, very useful. All right, that's it for trivia. Thanks for sticking with us. Hope you got some of those right. Whoever got the most right is going to get some astronomy swag sent their way. And then I think we're going to run through our announcements one more time before we close out. So let me pull that up. Here we go. All right, so no more trivia, but make sure you like and subscribe on our YouTube page here. Liking us and subscribing to us gives us a little bit more presence. We can reach more people. It's super helpful, so please do it.
And you can follow us on our assorted social media. On Twitter and Instagram, we are AoT _BCS. And on Facebook, we are AoT BCS. You can also keep track of our events at astronomyontap.org/events, as well as the events being hosted by the innumerable Astronomy on Tap chapters across the world.
Yeah, there's a lot of them now. You can also help support our usual venue, the Grand Stafford, at Jose-Quintana-20 on Venmo. Send a message that says Stafford Tip so that they know what your donation is for. But that's how you can tip your bartenders tonight.
And if you would like to support us, you can find us on Venmo and Cash App at AoT BCS. And if you send us $15, we will send you an AoT BCS shirt, just like the one MC's wearing. You probably have to say something to be seen right now.
MC. Hi, it's me. I'm wearing a shirt.
It's a very cool shirt featuring our lovely space traveler, like you can see on this slide.
Yeah. All right, our next event, we are not going to have an event in July. We're taking the month off. Our next event is going to be August 18th, the 3rd Wednesday of the month. And we are going to be doing a hybrid in-person and live streamed event. So if you can make it out to the Grand Stafford, please join us there. It'll be great to see people in person again. Make sure you're vaccinated before coming. And if you can't make it, we will still be live streaming the event.
I think that's it for the announcements.
Yeah. Awesome. Well, thank you all for joining us here. And we'll see you in a couple months.
At AoT BCS number 38.
Number 38. Bye.
Have a good night.